So today in this class, we are going to discuss about the query evaluation. That is the basically we'll be discussing from here on the query evaluation. But this is just an introduction, actually overview in this chapter that we'll be providing. I'll be providing to the query evaluation. Okay, because it's very important. See, whenever you are executing some query, how many pages are being retrieved? That means since pages exactly as you know that these are those data that is retrieved in terms of pages is basically from backend. So this is the IO operation. Okay, so the cost of operation lies with the number of pages that are retrieved from the backend. Okay, so since the databases are very huge databases that are being used for query for retrieving the data from the backend, that in this particular subject that databases that we are discussing are basically the huge databases, right? So when you execute a query, the efficiency of query matters, and that determines the efficiency of the system, right? So the minimum number of pages means the cost of query is low. This execution of the query is less, right? So it depends on how many IO operations the system is performing given a particular query is being executed. Before going into the discussion of all those things like the number detail of the evaluation algorithm given the different type of operators that are used in the query, okay, let us have a brief description of the system catalog, because it is all about the tables, the relations that you handled in the database. Okay, so in relational DBMS, the catalog means the table that actually handles the detail or the descriptions of the database. Okay, the different relations and attributes in the database. So the catalog basically has the components, the detail of the catalog. Let us discuss. And remember that these catalogs that are being used are itself actually the collection of tables. And description of this collection of tables is also included in the system catalog itself. And these tables, the catalog table, can also be queried like any other database table in the database. That is, any other relations in the database. So the informations, let us have a brief outlook or see about what are the informations that are actually stored in the catalog. Okay. So when we talk about information stored in the catalog, we must know that at the minimum the catalog stores the say the table names, okay, and the file name, actually the file name in which the table is stored in the backend. Okay, the file structure, like whether the file is stored in the as indexed or is in the heap file or something or like that, and it also has the attribute names and the type of each attribute, okay, in that particular table is also stored, is also described in the catalog table. Okay, so it is, apart from that, if any index is defined, that index is also being shown in the table itself. Okay, and the integrity constraints. When we say integrity constraints, like those like primary keys, right? The foreign keys, etc., are the integrity constraints. So detail of the integrity constraints are also stored as part of the table definition in the catalog. Okay. Apart from this, the table, there is for each index. Okay. For each index, the index name and the structure of the index. Suppose if it is a B+3 index, what kind of index or hash index, the structure is also stored there. Okay. So search key attributes for each index is also described in the catalog file. Apart from the table and the index, the view name and the definitions of view are also defined in the catalog. Okay. So these are the basic contents of the catalog, and in addition, there can be the catalog contents like cardinality, that is the number of tuples in the relation is the kernelity. Okay, size, the number of pages that are required to retrieve a particular table. As you know, the relations, the number of pages differs depending on how much data you are going to store in the particular relation. So it is those, those also define that that indicates the size, that is the number of pages that will be retrieved. So index size, what is the size of the index? That is the number of pages that involves the that index, and also the cardinality of the index, that is how many elements, unique elements are there, distinct elements are there in the index. Okay, so index height, it depends on the that description of index height is also given. Index height is nothing but actually non-leaf node from the counting from the root node to the leaf node. So when you count from the root node to the leaf node, the number of non-leaf level in the middle that you get is the actually index height. Okay, and then similarly you have the index range, which indicates the difference between the maximum value stored in the index and the minimum value stored in the index. That gives the index range. All those descriptions are stored in the catalog tables. Okay. So catalogs are itself stored, as I told you, the collection of tables. Okay. So it is, as you can see, there is a description of the catalog table itself, which stores the definition of the catalog. The catalog, catalog table, that is the which stores the attribute values, detail of the attribute values. Okay. So that is, suppose that particular table in the catalog is named as attribute underscore cat. As you can see here, it is the attribute underscore cat, and it has some variables, that is the attributes, which are, suppose that the name, okay, that is the attribute name. Similarly, to which relation the attributes belongs to, given by the, that you can see rel underscore name. Okay, and then suppose the type of that particular attribute, whether it is a string type, or whether it is an integer type, or whether it is a date type. Okay. So similarly, position, in which position the relation that particular attribute exists. So these are the four, suppose, the attributes of that catalog table, which is the attribute cat. Okay. Now there are two tables in the database. One table is indicated by sailors, another is table indicated by reserves. Sailors are the people who drives a boat. Okay. So here you have the SID to indicate the sailor ID, that is the primary key of the sailor. Okay. Then similarly the sailor name, which is a string, the name of a person. Then rating, how good the sailor is, given by some rating, say that rating value is stored in the rating. Okay. And age, what is the age of the sailor? Okay. Similarly reserves. Now reserves, here in the reserve table means a particular boat is being reserved for a particular day by some person. Okay. So here you have a SID, that is the sailor ID, boat ID, and the day indicates the composite primary key. Apart from that, the name of the person, that is the name of the person is indicated there. Okay, with a string value that is given by the name. Okay. Now these are the two example databases, example relations, which are stored in this database. Okay. Now in the catalog table that we have discussed about the attribute underscore cat, you can see that particular catalog table name. You have the attributes defined for these two tables, sailor and the reserve, as well as the catalog table itself. The attributes of the catalog table are also defined there in the same table. Okay, so it is basically any this one catalog table are like any other database table. Okay, now here you see the example here. The attributes of that particular catalog table, attribute underscore cat, are the attribute name. Okay, so to which relation that attribute attr underscore name belongs to? It belongs to the relation name, that is attribute underscore cat. Okay, and what is the type of that particular attribute? Is the string. Okay, where in the, what is the position of that particular attribute in that particular relation is 1. Okay, similarly the next is the relation name in that particular, next attribute is the relation name in that particular table. So relation name rel underscore name, as you can see, belongs to the attribute underscore cat. Okay, and that is that is also the type string, and that is the position is 2, right? Similarly the type is the third attribute, which is basically the type of that particular attribute, whether it is a string type or integer type, etc. Okay. So it is the that is the type string, and the position is 3, right? So position is the last attribute which is given by the integer. Okay. So that is the type is the integer and belongs to the attribute cat. Similarly, after that you see the continuity here. You find that the sailor ID, sailor name, rating, and the age that belongs to the sailor table. So after that you get the both ID, right? SID, sailor ID, both ID, and day and our name belongs to the resource table, right? So the positions are similarly separately indicated for each of the relations here. Okay. So this way the catalog table for the attributes here. Similar catalog table you will find also for the relation. Okay. So it's a catalog tables. Catalog itself is actually system catalog itself is a collection of table that describes the database itself. Okay. So this is an example catalog table for only the attributes, okay, of the different relations. So here you find this particular values, this particular tuples. These are the tuples which are stored in the catalog table. So catalog table describes all the tables in the database, okay, and the catalog tables themselves, okay. That is, so it basically essentially describes all the data that are stored in the database, okay. So when you need any information about the tables in the database, you need to obtain it from the system table, okay. That is the system catalog. So so catalog table is actually also it behaves like any other table. That means you can use any kind of query then as you use in case of the normal databases. Same way the queries can be written for getting information from the catalog table, okay. So it directly applies to the catalog table. So this is all about what are the information stored in the catalog table. Now going to the introduction to operator evaluation, okay. That is, how do we evaluate the operators? When we say operators, we will be basically discussing about the relational operators. You understand the relational operators? These are less than, equal to, greater than, equal to, greater than, right? So these are the relational operators. So there are 3 common techniques which are basically used in the developing of the evaluation algorithm for relational operators. You know where the relational operators are used in the query, right? It is used in the where clause, you know, where you write the relation name dot attribute name greater than or equal to some value, okay. That way you write the query. So here in the where clause you can have one relation name with the attribute name, or you can have multiple relation names. Suppose if you are considering the join operation, then you need to have 2 different relations with the some attribute name where you are joining, okay. So that way you can have multiple relation also in the where clause using the relational operators. Now there are 3 common techniques which are used for developing the algorithms for relational operators. The first technique is indexing, okay. In the when we use the indexing to develop the evaluation algorithm for relational operators, we are basically use the indexing in the join condition. That is, if a join condition is specified, then we use an indexing to examine just the tuple that satisfies that condition, okay. Suppose if a join condition is specified in the where clause, you find that there are 2 relations which are being combined, then you can have the if you have an index, you can of any of the attributes of that particular the joining condition, then you can use the that particular index to make the query more efficient, because index, you know, to get the index, it is much faster than to get the actual value from the database, okay. So so index files are accessed easily, right? They are accessed faster. And so if you have an index defined on that particular attribute, then you can take help of the index to develop the algorithm. So that is one technique. The second technique is to go for the iterations. So if you do not have an index there, so in many cases when you are trying to retrieve lot of tuples from the relations, then input tables, then you need to execute the tuples one after the another, that is to retrieve the tuples one after the another by using the iteration method. Okay. So if we have to use only few fields from the each tuple, and if we have an index defined while doing the iteration operation, then of course we can use the we can take help of the index to get the tuples there. If we want only few attributes from the tuple and we have to retrieve the the tuples, okay, then we can if there is an index for those few attributes that we want to access, then we can obviously take help of the index there. So another technique for evaluation of the operators, relational operators, is partitioning. Okay, so it is the in many cases actually we need to partition the data to get faster execution of the queries. Okay, suppose if we want to access some particular elements from a particular part, if we partition it in terms of by sorting the data, then it becomes easier. So for those kind of queries where you need to have such kind of faster execution, we can take help of the technique which is called as the partitioning. So here we can use two techniques to develop the partitioning algorithm. That is, one is the sorting, because if we sort the tuples in terms of some attributes, then obviously the same elements will be combined. We'll have a block of those data which are of the same value, right? So we can easily get it, because in a binary search also we do such kind of thing, right? So that binary search becomes easier for us to search. So in the same technique actually here we use, that is the partitioning of the data based on either sorting or hashing. Okay, we can use sorting or hashing to implement the partitioning. So these are the three techniques, that is the indexing, then your iteration, and then your partitioning. These are the three techniques which are used to develop the algorithms for relational operators. Okay, so now after discussing these techniques for developing the relational evaluation algorithm, that is for developing algorithm for the relational operators, now we can have a detailed look about it. Okay, so let us look about the access path. What is called an access path? Okay, access path is actually, when you say access path, it is nothing but different ways of retrieving the data from the table. Okay, so if we use multiple ways, say, of retrieving data from the table, okay, so these different ways that one varies from the another are the different access paths to get the data. Okay, so it is the so an access path actually consists of either of the two techniques. One is the file scan. You can go for the detailed file scan from first to the end. Okay, or you can have an index plus that matching selection condition. So when we have an index defined on some attributes, some set of attributes, we can take help of the index, provided that the selection condition matches with the index. Okay, so either of these two can be used to get an access path. Now, so as I told you, that every relational operator, the operator that you use in the where clause of the queries, either use a single table, that is on one side you have a table for which you are comparing the attribute with some value, or you can have more than one table, that is where you are combining, or you can actually comparing the value from one relation with another relation. So you can have a one or more table defined there that is, you can use one or more table to get the values. Okay, so access method that we use to retrieve tuples contribute significantly to the cost of the operators, because the way you define how you are going to use the access method for those tuples and the tables and the attributes that are defined, that basically determines the cost of that particular operator. That means how much data you are going to retrieve, that determines, and how it is stored in the backend, that determines the cost of the retrieval. By cost here, I mean to say the number of I/O operations that you need to execute to get those data from the backend. And that number of I/O operation means the number of page retrieval, where the data is stored. Now, when we use the access operations with the relational operators which are used, then basically it is nothing but something where you have the attribute of value, right? When you have an attribute, operator, and value. Okay. So when we have an attribute, say this attribute belongs to some relation, right? This value belongs to the domain of the relation, and this is the operator, relational operator, that you are using or connecting with the values, with the attribute, right? Attribute thing. So it is, and for having a proper access path, how the DBMS software basically determines is that it transforms those relational operators to a conjunctive normal form, okay? An expression of conjunctive normal form. This is commonly called as the CNF. That is it is basically defined as the conjunctive normal form, okay? CNF. So what is a conjunctive normal form? It is nothing but actually the different conjuncts. A conjunct means where you use a relation name, one or more relation name, and a relational operator. That is one conjunct. Then you have the conjunction, that is the AND operation in between, and then there is the another conjunct. Okay, so you can have the number of conjuncts sequence by using AND operations in between. Okay, so once you have a conjunctive normal form defined for different relational operators that you use with the where clause, you can use different ways the indexes at different access paths, okay, to retrieve the tuples, okay, with the matching conditions. So the selection conditions can be based on matching of the index. If it is suppose the hash index, when we need to use the hash index. If it's the tree index, when we use the tree index, that's what we are going to discuss here. That is, given the conjunctive normal form, that is, you see the particular access path. See, the file scan is very simple. That is just scanning the file from one into the another. Okay. So basically, on which part we are concentrating here is the number 2. That is an index plus a matching selection condition. Okay. So here we will be basically discussing about the index that you are using to retrieve the tuples, that is for that particular access path, okay, given a selection condition. Okay, so file scan we are not going to discuss. The second part, the index only, we are going to concentrate on in conjunctive normal form. So it is in the if the CNF matches, CNF matches a particular hash index, only if the values are like, if you have the equality condition defined for every value. That is the attribute here, that is the operation that we use here. You can see this operation. The operation is replaced by the equality sign. So for every conjunct, when you have such equality conditions defining the relational operators, then we can use the hash index. Suppose provided the hash index search key value matches with that particular selection condition. Okay, that conjunct. So if the conjunctive normal form, every attribute conjunctive normal form have a equality condition and it matches with the hash index search key values, then we can use the hash index, and it will be faster if we use the hash index to retrieve the value. Okay, so it is, suppose for example, if you have rname, SID and BID as the search key value for the hash index. Okay, rname, say we are writing, it's okay, rname, SID and BID, and suppose we want to retrieve this value, that is the rname equal to zo, and rname equal to zo rname equal to some value named zo. Okay, see, this is a conjunctive normal form, this is in the conjunctive normal form. Okay, so BID equal to some 3, okay, and SID equal to 5. Okay, if we have a conjunctive novel form, okay, that is the these values, okay, then we can basically use the, see, there is a equality condition in between every values here. You see the equality conditions here. Okay, so this fits the condition that is required for using the hash index. Okay, and we have a hash index defined on these 3 attributes, rname, SID and BID. So everything matches here. So it's basically when we are trying to execute a query to retrieve these values, then we can go for the hash index. Hash index is the most appropriate one. Okay, but you can have, so for any other condition for the search key, such as if you have only part, suppose if your query has only this part, rname equal to zo and the BID equal to 3, okay, then probably then you cannot use the hash index, because you have some attributes more than this, you know, defined in the hash index file, right, for the search key value in the hash index. So you cannot have the, if the partially it is matching, you cannot use the hash index. Okay, similarly for the tree index, when the tree index matches a CNF selection, okay, and if there is a value, if there is a term in the form of attribute of value, okay, and for each of the attribute in the prefix of the index search key. Now if we have a index defined as this rname, SID, BID, now what are the prefix here? Prefix, like, you know, rname is one prefix, rname, SID is another prefix. So for the prefix, if it matches, like in case of hash index, every term, every attribute has to match with the attributes that is in the search key. In this case, only prefix has to match. If prefix matches, then obviously we can go for it for the tree index. Okay, otherwise not. That is, if your if your query consists of rname and BID, this one, we cannot use the tree index. But if you have rname and SID, okay, if we have rname and SID, we can go for the use of tree index. Okay, because rname and SID is a prefix. Okay, but if your query consists of, suppose, BID, SID, you cannot go for, because BID and SID are not the prefix of the search key. Okay, so that depends on the prefix of the search key. If it matches the prefix, then you can go for use of the tree index. Finally, if you have a hash tree or a B tree defined for a particular relation, and if you are writing a query, if you face a query where you are trying to retrieve some values which are beyond that scope of the search key, okay, then what you can do, you can use the appropriate index to get the subset of that particular search key filtered. Okay, those tuples which are being there as the, which are filtered by the subset of that particular search key, that can be, the index can be used to get those values, and then you can go for matching of the non-index part with that, okay, to get the actual data. So suppose, for example, if you are using this, if you have suppose only SID and BID in the search key of the index, okay, and if you have to retrieve something like, rname equal to zo, this, and BID is 5, okay, say this is BID and SID, and SID equal to 3, okay. Now you can take help of either hash index or the tree index, whichever way it is defined there in that particular relation, okay. This, if the index file happens to exist there, then you can take help of this particular index on this to get this part, that is the filter out those tuples which matches this by using the indexes, and then you can actually match with the actual, this non-index part with this one, with this, and you can get the actual number of tuples or actual tuples which are being retrieved by using this non-index part, this matching the non-index part with the retrieve values for the index part, okay, and you can get the elements there, data. So that way it will, when you match this non-index part there, it will eliminate some tuples from the earlier list where you have used the index part, okay. Now given this access path, the definition of access path, I hope you have understood what is an access path, right? So have you understood what is an access path, right? So it is, since you have this, given this access path concept, we can find out the selectivity of access path. That is, selectivity of access path means it is the number of pages that is being retrieved when you have used a particular access path to retrieve all the desired tuples, okay. So when you are using the access path to retrieve some desired tuples, given the condition, given that access path, then selectivity means that the number of pages that you get to retrieve from the backend, okay. So if a table contains an index that matches a given selection, okay, then there are basically two access paths. One where you use the index, and another where you scan the data file, okay. So there are two access paths when a table contains an index that matches the given selection, okay. So now we can have the selectivity by defining, we can have a particular additional term over and above the selectivity, is that it is the most selective access path. What is the most selective access path? That is the access path actually that gives rise to selection of fewest number of pages. That is, when you retrieve fewest number of pages, that is the least number of pages given a particular access path being followed, that is called as the most selective access path, okay. So obviously this selectivity of the access path depends on the primary conjuncts that you use in the relation, okay, and as you can find out from here, whatever we have discussed till now, that is each conjuncts what it does. See, each conjuncts here, when you write rname equal to zo, when you write, suppose forget about the other part, you just think about the rname equal to zo. What it will do? It will filter out all the tuples in that particular relation, with the name zo, right? So basically what this conjunct is doing, it is filtering out some elements. Similarly, BID equal to 5, the same thing it is doing. It is filtering out some tuples where the value matches, that is BID equal to 5. SID equal to 3, sailor ID equal to 3, that is, it will filter out those tuples which has the Sailor ID 3. Okay. So basically it does every conjunct filter out some tuples from the relation, and then when you use the AND operation, that's the conjunction operation, you get the that is the when both the cases matches, both the conjunct filtering of the out of element filtered out elements of the one conjunct is matched with the filtered out elements of another conjunct to find the intersections, right? That is what the conjuncts do. Now here, so the fraction of tuples in the table that satisfies a given conjunct is called as the reduction factor. So when you filter out that way using some conjuncts the elements of the table, the factor of that is the fraction of tuples in a table that satisfies that particular given conjunct is called the reduction factor of that particular conjunct. Okay. So what is the reduction factor here? It is nothing but the fraction of tuples that gets selected. Okay. That is, or that satisfies the conjuncts is the reduction factor. Now, algorithm for relational operators. Okay. So those algorithms which are used to get the values for the relational operators, okay, that is for the to have the proper access path get selected, are are the selection, then projection, right? Selection means the selection condition in the where. Okay. So we are going to discuss first about the relational operators where it is being used for the selection, that is the less than equal to, greater than equal to, etc. So one where you already that is the directly scanning the file, okay, for the given conjunct. So when you have a conjunct being defined, conjunct is nothing but the R of this one, this is the conjunct, right? So when you have this conjunct defined, you can go for scanning the entire file that satisfies the conjunct value. Okay. So now, if you have an index, if you are not scanning the entire file, and if you have an index, there is an index for that particular relational operators, that particular attribute that particular attribute that is used with that relational operator, then we can use that index to retrieve those elements. Now, suppose if you have a selection condition, suppose a selection condition retrieves 10% of the tuples in the result, and there are some 100 pages using 10,000 tuples retrieved, okay, and suppose we have a clustered tree index defined for that index file, then you know what is a clustered index. In the first unit itself you have studied what is a clustered index. Clustered index is basically where the order of the index keys matches with the actual order, the way it is stored in the backend. Okay, the way data is stored in the backend is in the same order in which the keys are arranged in the index file. Okay, so that is the clustered index. So it is. So if you have a clustered index, B plus 3 clustered index, then we can retrieve the qualifying tuples with 100 IOs. It will take the very least number of IOs. So to retrieve the 10,000 element, we can have as little as 100 IOs only. Okay, and also in addition, few IOs to traverse from the root of the B plus tree to the leaf of the B plus tree. So this with a few IOs for that, and plus the 100 IOs for retrieving the data. Now, if the tree is unclustered, then obviously we can have at most 10,000 different IOs if we have every data that is being retrieved in a different page. So for every page you need one IO operations to retrieve the page. So if every data of the 10,000 is stored in different pages, then we require 10,000 different IOs. Right? That is the worst case scenario. Now, when the relational operators is used in the normal selection condition, this way the operations of the algorithms can be designed. Okay. So projection is another way, another commonly used techniques with the relational operators. We know the projection, that is where you have a subset of attributes being retrieved from the entire attribute set, right? So if you do not have a distinct keyword defined for the projected attributes, then obviously you don't have to do anything. You just have to simply retrieve the data, right, by scanning the table. So you can use simple iteration, that is scanning of the table, or you can use an index of those keys containing all the necessary fields. Okay, so either of that can be used if you do not have to use the distinct elements. Because see, when you are projecting a subset of attributes, if it can have duplicates, if the primary attribute is not included there, primary key is not included in that attribute set, then you are likely to get a lot of duplicate values. So those duplicate values, if you are not bothered about duplicate values in the result set, then obviously you can go for direct retrieval using scanning of the table, or you can use the index to get the necessary data. Okay, if it supports some index. So if we have to eliminate duplicate, then what we need to do? First, suppose if you are retrieving SID and BID, okay? Suppose if you are retrieving SID and BID, these two sets, okay? Then you are basically, if you don't want the duplicate values for SID and BID, then what you need to do? You need to first retrieve all the elements by using some techniques, either using index or non-index, whatever it is, either by file scan or by using some index if it is defined on index. Then after retrieval is done, all those tuples which are being retrieved, those must be sorted. Now when you do the sorting here, what happens? Those elements which are common, right, in the sorting, they will appear together. So you can remove the duplicates. Okay. So after that, the duplicates can be removed when you have the same values for any two of the rows. Okay. So adjacent rows can be eliminated there. The third is the join operation. So join operation occurs when you have something like that, you know, in the selection condition, in the where clause, suppose if you have, as you can see, the reserved.sid is equal to sailor.sid. Okay, that is reserved.sid is equal to sailor.sid. So here on the SID field, it is joining, right? Now suppose you have an index defined on the SID of sailor, and you don't have the index defined on the SID of reserves. Okay, so what you can do, you can retrieve the elements of the sailor table by using the index. Okay, and then probe those elements against the SID of the reserve. Okay, so you can have the matching elements of the SID of the reserves once after you retrieve using the index. Okay, so scan the sailor on that SID column, and then you probe it with the index, with the tuples that you retrieve from the non-index part. Okay, so that way so this technique is called as the index nested loop join. Basically, this algorithm, this approach is called as the index nested loop join. Another way of doing, suppose if you do not have an index here, so in another way of doing is that you sort both the relations, reserves as well as the SID, as well as the sailor on the SID column. That is, on the attribute of the SID attribute, you sort both the relations. So when you sort, you get the corresponding element and then you merge. Okay, so that becomes another technique, because when you sort on the SID value, for the same value there will be consecutive tuples. Okay, so both sides can be merged and you get the resulting join condition. So this is called as the sort merge join. Sort merge join, as you can see the name sort merge join. Okay, the other operations apart from these three operations that we have discussed, other operations like group by aggregation can also be you can develop algorithm for those also. Okay, now for the group by, if you have a corresponding index for the attributes on which you are using the group by, okay, then you can use that particular index to get the group by done. Okay, so it is the so index can be used to get the appropriate order without explicit sorting. Either you can use sorting or you can use the index to get that is you can use the index to get the elements in the sorted order. So similarly, aggregate operation is another common operation, special operation which are required in many queries. So for the aggregate operations also the algorithm can be used to develop, where you can use the temporary counters in the main memory as tuples. That is, the temporary counter in the main memory as tuples are retrieved. Okay, to get the aggregate done. So in the memory itself, you can use a temporary counter as the tuples are being retrieved. It can perform the aggregate operation on that particular temporary counter. Okay, so that way it can be done. So this much is about the basic, that is the overview of query evaluation. That is the initial part of the query evaluation technique. Okay, hope you have understood this lecture. Okay, if you have any doubt, please ask me. Okay, it's always welcome. Actually, we can discuss all those matters. Please ask me whatever doubt you have. So after this query evaluation, we'll go for the optimization. That is, how do we go for optimization of the queries? Okay, so this is where we do the evaluation. Okay, that is how to evaluate the queries. Now, how to optimize it? That is the next concern. Thank you.